So let's talk about congruence-modulo-an-ideal. So before going through this topic, it is very, very strongly recommended that you go back and review what we learned about equivalence relation. Because here is the basic definition. Let R be a ring and let I be a two-sided ideal. Given this data, a ring and an ideal, by an ideal we mean two-sided ideal, always, if I don't say otherwise. So a ring and a two-sided ideal, we are going to define an equivalence relation on the ring R. And the relation is called congruence modulo the ideal I. Okay. So it's crucial that you go back and read up now, if it has become hazy, what equivalence relation is and the example that we saw of it. And we'll see that example again, actually. Okay. So here's the definition. Let R be a ring, I be an ideal. We say that A and B, two elements of the ring, are congruent modulo I if the difference of the two elements simply belongs to I. And we'll have a notation for this. If A and B are congruent modulo I, we'll just say congruent mod I, then we write that's the notation. That means A and B are congruent modulo I. You read that by saying A is congruent to B modulo I. So the lemma that you want to immediately prove, once you have this thing, is that the congruence modulo I is an equivalence relation on R. Congruence. So the setting for the lemma is still this. Let R be a ring and let I be an ideal. Given that, congruence modulo I is an equivalence relation on R. What this means concretely is the three following things. Being a relation means that it has to satisfy three properties, this relation. Every element is congruent to itself. If A is congruent to B, then B is congruent to A. For all A, B in R. And 3, if A is congruent to B and B is congruent to C, then A is congruent to C. For all A, B, C in R. And these are the three properties for a relation to be an equivalence relation, if you remember. Every element has to be related to itself. That's property 1. It's called reflexivity. There are these names, reflexivity. This one is called symmetry. If A is related to B, then B is related to A. And this one is called transitivity. If A is related to B and B is related to C, then A is related to C. Okay. And the proof is very straightforward, actually. What do I want to write? Maybe let's just do a little doodle here and check that this lemma is true. I'd leave you to write it out. A is congruent to A mod I. What does that mean? I'll remind you, two things are congruent. Modulo I simply means that the difference has to be in I. This means it amounts to saying A minus A is in I. Is that true? Well, A minus A is 0. Of course, that's in any ideal, because an ideal, after all, is a subring. So it contains 0. Okay, so that's true. If A is congruent to B, meaning A minus B is in I, then B minus A is in I, because B minus A is just the negative of A minus B. And again, I is a subring, so if it has an element, it has its negative. But if B minus A is in I, then B is congruent to A. Okay, as simple as that. If A is congruent to B and B is congruent to C, what does that mean? That means A minus B is in I and B minus C is in I. So then the sum of these two things is also in I, because I is, after all, a subring, so it's closed under addition. So if you have two things in I, their sum is also in I, but this sum, note, is just A minus C. A minus B plus B minus C is just A minus C. So A minus C is in I, and that just means that A is congruent to C. Yeah, so this is property 1, this is property 2, this is property 3. Okay, well, that's the lemma, and I'll introduce a little more notation given this setup, and then we'll do the example that you must be recognizing already. We have seen something like this before when we talked about congruence modulo an integer. So we'll do that example again in detail, because indeed this definition is generalizing that construction.